Welcome back. In this section, we're going to start looking at exponential functions finally. More specifically, we're going to start looking at the natural exponential function e to the power of x. We'll eventually get to talking about all the logs and all the other exponential functions, but first we can actually define e to the x now, and that's because we came up with our definition of natural log as a definite integral, and we came up with the discovery of all of its properties, including that our natural log function that we defined would be a strictly monotonic function, always increasing, and that meant it was one-to-one, which meant it had an inverse. And so now that's what we're going to define. We're going to define e to the x as being the inverse of natural log. So since they're inverses, that means that if you knew that e to the b was equal to some mystery number a, then that would mean that natural log of a would be that mystery number b, and vice versa. If you know natural log of a is b, then you also know that e to the power of b is a. And that's just our inverse property that we had from back in 5.3, that if ab is a point on the graph of f, then ba is a point on the graph of f inverse. The other bit of good news here is we already know domains and ranges. For the natural log function, its domain was things that were positive, range was all real numbers, and we remember for inverses, they switch domains and ranges. That means for the exponential function, its domain is all real numbers, and its range is only positive things. So here's kind of an important part to think about, and it's maybe something you haven't cared that much about up until now, which is the real number exponent problem. So the problem here is back in your high school days, you originally started to talk about exponents in terms of repeated multiplication. So at some point, somebody would have said 3 to the power of 5 meant 3 multiplied by itself 5 times. And eventually we came up with other ways to explain other kinds of exponents. Negative exponents meaning a reciprocal, fractional exponents referring to some kind of a root. So as far as in high school, you have a reasonable way of explaining what a to some rational power is. We know that whatever that power is, if it's a fraction, then that meant you'd be doing some sort of a root and some sort of a power. And we know what all of those mean if m and n are counting numbers, if they're natural numbers. So even if you had a funny thing like 3 to the power of 1.41, you could rewrite that as a fraction, 141 over 100. So if you said, what does that mean? I'd say you're taking 3, you're taking the 100th root of it, and then raising it to the power of 141. And it's whatever that is, it's some kind of a number. But if you ask me what 3 to the power of square root of 2 is, that's a harder thing to explain. Like, what does raising things to a power of root of 2 even mean? So we really haven't had a good way of explaining that up till now, except now we do. And that's courtesy of what we said on the previous slide, that we know that since the range of natural logs is all real numbers, then e to the x is defined for all real numbers, which means things like e to the square root of 2 would definitely be something that's a real number. And actually, we can now say what e to the square root of 2 means. Specifically, since e to the square root of 2, that e and natural log are inverses, then whatever the e to the square root of 2 is as a value, that's the number where natural log of k is square root of 2. And we know that natural log of a is square root of 2 somewhere because square root of 2 is in the range of natural log. So at some point, natural log will be equal to square root of 2. And so wherever that point is, that is e to the square root of 2. Other things just to mention here, and some of this is, again, obvious stuff because of being inverses. We know that when you have two functions that are inverses, if we put f inside of f inverse, they'll cancel each other out, or if you put f inverse inside of f, they'll cancel each other out. So in terms of natural log and e, putting a natural log inside of e is e to the power of natural log of x. They would cancel each other out, leaving you just x. And if you had natural log of e to the x, the natural log and the e would cancel each other out, leaving you with just x. There is another little notation, though, that's important to know, and this is one that you'll frequently see for typing purposes. And that's because, when you're looking at writing an e to a power, if the power is really big, as it currently is here, this e to the x squared minus 3 over x minus 1, it can be a little bit ambiguous for that fraction. Is the x minus 1 on the same line as the e? Is it part of this fraction? It could be a little bit confusing. And so one way that we can make it easier on ourselves is using an alternate notation, which is writing exp and then in brackets whatever the power of e to the power of is. So you'll frequently see that. Textbooks will have that sometimes if the answer to some function is e to some terrible power. Instead of writing it as e to some terrible power in a tiny print, they'll write it as exp in brackets, and the terrible power will be there. So now that we have these inverse properties for our exponential function and our natural log, we can go ahead and start solving equations with logs and exponential functions. Because if I know that 3 to the e to the 3x minus 1 is 17, then I know that natural log of 17 is 3x minus 1. And then if I feel like it, I can go ahead and solve for x. And I have x is 1 plus natural log of 17, whole thing divided by 3. And similarly, any natural log equation I can now solve, because if natural log of 3x plus 2 is negative 2, then I know that e to the negative 2 would be 3x plus 2. And then kind of in the same way, I can go ahead and solve for what x is. So again, we haven't yet talked about the other logs or the other exponential functions, nor have we actually established that this exponential function e to the power of, that our usual power properties would apply. And so that's something we probably are going to want to square away fairly soon. Before we get there, though, we've got ourselves a function f of x. It's this natural log function, and we want to find f inverse. Here I say at the very end, then find the domain and range of both functions, but actually I think I'm going to find the domain and range first, at least for f. I know it's a natural log function that's had some transformations applied to it, so I know whatever it is, the regular natural log of x will have a range of all real numbers, no matter whether or not I do things to the graph horizontally or stretch it vertically or move it up or down. So my range for f should be all real numbers. As far as the domain goes, though, I need this 2x minus 7 to be greater than 0. So in other words, I need x to be bigger than 7 halves. So for my domain for this function, I would say the domain for f is things that are larger than 7 halves, not including it, and the range is all real numbers. So that means I can say in advance now, f inverse should have the domain of all real numbers. And it should have a range of things that are larger than 7 halves. Okay, so let's see if we can show that we've got ourselves our inverse function, and let's find out what it is. No surprise, I mean, this is some sort of transformed natural log. We're going to get some sort of transformed e to the power of function, but let's just see what we get. We start with our function, y equals 5 natural log of 2x minus 7 minus 2. And the next thing we do is, as always, we switch our x's and y's, and then we solve for y. So we're switching x and y's means I'll have x equals 5 natural log of 2x minus 7 minus 2. And now I'm going to just start, not 2x minus 7, 2y minus 7. Try that again. So of course, we switched the x and y, so whatever was an x is now a y, and whatever was a y is now an x. So I'm going to isolate my natural log. So I brought the 2 over, and I've divided by 5. And at this point, now I can rewrite things. I have natural log of something equal to something else, which means this can be rewritten as an e to the power of, in this case, e to the power of x plus 2 over 5 equaling 2y minus 7. And then the only thing left for me to do is bring the 7 to the other side, then divide by 2. And once I've done that, then I now have found my inverse function. So now I can conclude that f inverse should be e to the x plus 5, x plus 2 over 5 plus 7 all over 2. And there we go. We found our inverse function, which, as expected, this was an exponential function. If we looked at this and thought about it in terms of transformations, we would see it's an exponential function, and one of the things that was done as a transformation was a vertical shift upwards by 7/2, which is why our range is things that are larger than 7/2 rather than things that are larger than 0. Okay, so now let's actually prove. These are things that we know from before should work for things with at least rational exponents. But as I said before, real exponents have always kind of been a problem. We had no real good way of explaining what e to some real number power, or 2 even, to some real number power might mean. So how do we know that these properties should work for real numbers a and b? So now, good news, I can confirm that these customary properties that we normally would have for any other base and for rational powers will work at least for e for real number powers and for any real numbers a and b. And so for this, I'm going to take a look at the first one and say, we know e to the ab. If I were to take the natural log of it, I could definitely do so. And that's because I know that whatever e is something positive. So a natural log of that something positive will exist. And because of my inverse properties, natural log of e to the a plus b is just a plus b. And I'm just going to call this little output here, I'm going to call it number 1. Now, if I take a look at the other side of the equation here, if I look at e to the a times e to the b, that's also going to be something positive times something positive. I could take natural log of that. And I've already proven before that natural log has the property that natural log of two things multiplied is natural log of the first thing plus natural log of the second thing. And then because of our inverse properties, natural log of e to the a is a, and natural log of e to the b is b. And you might be saying to yourself, well, okay, that was nice. Why did you bother taking derivatives? Why did I bother taking natural logs rather of things? And that's because I have a thing to remind myself of, which is natural log is a one-to-one function. So what I've looked at here is for this particular input, the output was a plus b. And for this particular input, the output was also a plus b. So the first thing I notice is the outputs are the same. So I'm writing something down that feels kind of silly to say that a plus b equals a plus b. In other words, I'm saying that the output from the first equation and the output in the second equation are the same. So that means that the inputs for the natural logs must have been the same. And that's because natural log is a one-to-one function. So because it's one-to-one, remember that one of the things that we said for a definition of one-to-one was if the outputs are the same, then the inputs must be the same. So we've just concluded that for natural log of a plus b, that it gets the same output that natural log of e to the a, e to the b did, which meant that the inputs must be the same, and there we go. We're going to prove the second statement in much the same way. So I'm going to do natural log of each expression, the one on on the left side, the one on the right side. And then with my log properties, it's going to show that I have exactly the same output for both, and so I'll make the same conclusion that I did for part 1. So let's do our proof for part 2, and this one I'll do a little bit faster. If I were looking at the first side of the equation and said natural log of that, natural log of e to the a minus b, that's certainly a minus b. And then I could do the same sort of thing for the right side of the equation. So if I were looking at natural log of e to the a over e to the b, my natural log property says that's natural log of e to the a minus natural log of e to the b, which is a minus b. I'm not going to explain as much as I did for the previous one, because the idea is the same. Since the outputs are the same, since a minus b and a minus b are the same, then that must mean that the inputs must have been the same, because natural log is 1 to 1. So now we can use our exponential properties for any real number exponent, which is actually kind of a nice thing to say, even though we had trouble coming up with a meaning of what does an exponential power, a real power mean. Now we have a way of defining what real powers mean, and now we can use e to the real powers in the way that we'd like to. There's one last little thing I wanted to say before we have a pause, and that's that we've got a lot of properties that we already know the exponential function will have, plus one more that we'll know very soon. The first parts that we know about this, we already said the domain and range, and we got that again knowing that e to the x was the inverse of natural log. So because we knew what natural log's domain and range was, when we switched them, we had the domain and range for e to the x. Similarly, we had that theorem that said if a function is continuous and increasing and 1 to 1, then its inverse will exist, and it will be also 1 to 1, and it will also be increasing, and it will also be continuous. So since e is the inverse of natural log, and natural log was continuous and increasing, then so is e. The last part, that's one that we haven't proven yet, but it's also probably not a big surprise if we remember the relationship between graphs. Remember that when we're graphing a function f and a function's inverse, that the two functions look like they are reflected in the line y equals x. We know what the graph of natural log looks like. It's something that's concave down. So it's not a big surprise that if I were to reflect this graph in the line y equals x, I would get something that's concave upwards. That's at least the intuitive idea behind it. The actual proof of why is it concave upwards, that'll be very apparent once we find out what the first derivative and therefore second derivative of e to the x is.